Welcome to Study Loop.
Hello everyone, today we're doing chapter 14, problem 6, and this problem asks us how many proton NMR signals will we expect from each of the following compounds. So remember, your NMR signal will depend on how many unique, chemically distinct protons exist in the molecule. So if we determine the number of protons and where they are located in the first example, we know that the terminal methyl has 3 protons. This center here has 1 proton going down, and this carbon here has 2 protons. This terminal methyl has 3. So we also know that protons that come off of CH2s, these 2 protons can be chemically distinct if the molecule contains a stereogenic center. Stereogenic center means a chiral center. Chiral center is a carbon that has 4 unique substituents bound to it. So we know that this carbon here is a stereocarbon. So therefore, most likely when we do our analyses, we will determine that these 2 protons are actually chemically distinct and exist in separate microenvironments. But let's go and start from one side of the molecule and working our way to the next to determine how many chemically distinct protons we have. So we can start from the left side. So on the left side, we see that we have an achiral carbon here. It's bound with 3 protons, and these 3 protons, you can say that they are free to rotate about the sigma bond. So we can assume that these will all be chemically identical to one another, therefore producing one signal in the HNMR spectrum. Next, we move on to our chiral center. In this chiral center, we have a chlorine and a proton. And obviously, we know that this proton, being in its own unique chemical environment, will produce a separate unique chemical shift signal in our NMR spectrum. Now let's look at the proton adjacent to it, which are this CH2 protons. So if we see here, we can see that the upper proton is cis to this electronegative chlorine atom, while the bottom proton is trans to this electronegative chlorine atom. And what we know about electronegative atoms is that they withdraw electron density away from your hydrogen nucleus. So it actually makes your hydrogen less shielded. And when something is less shielded, we know that it will require a lower amount of energy to cause that spin flip and resonance. So it will be downfield in our NMR spectra. However, something that is trans is going to be further away, so it's going to be feeling less of that electron density pulling effect from this electronegative atom. So there'll be more electrons isolated and localized around the hydrogen's nucleus, therefore causing a higher amount of energy to cause that spin flip. So it's going to be more shielded to the right side of our spectrum. So we know that the top proton must be chemically unique from the bottom proton. And then once again, we know that these 3 protons can spin around its sigma bond, generating all one signal. So we have 1, 2, 3, 4, 5 unique protons in this example. So now if we look at the second example, we see that this carbon here is a stereogenic center, and we have a CH2 here. So there's a good chance that these 2 protons will be unique once again. But before we do that, let's just draw out all the protons we have in this molecule. So we know that typically terminal carbons with their 3 protons can spin around the sigma bond, generating some sort of blurred effect and generating just one signal for these 3 protons, as these will all be equivalent and can be considered identical. So we have one terminal carbon here and one terminal carbon here, so we will have 2 signals from those 6 protons. And these 2 will differ from one another, but they will be identical within the same carbon. And obviously, if we move down to this carbon here, we see that this proton is in its own unique little environment. all by itself here. And once again, these protons off this carbon, we see that this proton here is cis to our electronegative chlorine and also to our methyl group here. However, this proton here is trans to our electronegative chlorine and also trans to our methyl group here. So we know that these two must exist also in this unique environment. So once again, we have 1, 2, 3, 4, 5 unique NMR signals from 5 unique protons. So now let's investigate these ones here. So if I were to draw out all my protons, I identify that this carbon here is a stereogenic center, and we have one CH2 here and one CH2 here. So these 4 protons most likely will be chemically distinct, but let's just work through it to confirm that. So once again, what we know is that these terminal carbons, these methyl groups at the very end, they produce one signal for those 3 protons. So we can just right away say that this is going to be one signal, and this is going to be one signal. And that's because of this free rotation and kind of blurring effect you see with those 3 protons. We also know that the proton in the stereogenic center will be unique. It's on its own little microenvironment right here. And we also see that we have a CH2 right adjacent to our stereogenic center. So we know the top proton is cis to our electronegative atom halide, and our bottom proton is trans. So these 2 protons, once again, must be unique. But now what about the second CH2 here? Well, this CH2 is now 2 carbons away from our bromine, while this CH2 we just finished was only 1 carbon away from this bromine. So clearly this CH2 that we're investigating now is going to be in a unique environment than the CH2, those 2 protons we just finished analyzing. So we see that once again, the CH2, this proton on top, is 2 carbons away from being cis to bromine, and this proton on the bottom is 2 carbons away from being trans for this bromine. So these 2, once again, must be unique in its own unique chemical environment. So overall, what we see is that we have 1, 2, 3, 4, 5, 6, 7 unique NMR signals from 7 unique protons.